To see the cool theorem that I want to talk to you about in action, we only need to know one piece of terminology, and that is called the floor function, which some people refer to as the round down function. This function takes in a real number r and outputs the greatest integer less than or equal to r. So for instance, if we were to try to floor 7.6565, we simply find the largest integer that's less than that, in this case 7, and we say that the floor of 7.6565 is 7. We pretty much chop off the part that comes after the decimal point. Likewise, we can put any real number on the real line and round down from there. So the floor of square root of 2 is 1, the floor of e is 2, and the floor of pi is 3. Armed with that terminology, we can now get to the trick. So, to perform this theorem, start with any irrational that you like greater than 1. For our purposes, we'll choose the irrational x is square root of 2. Next, what you're going to do is you're going to compute the integer multiples of the irrational. In this case, we'll compute the integer multiples of the square root of 2, but we'll floor each one, so we'll round each one down. And we get the corresponding integer sequence, 1, 2, 4, 5, and so on. If you look carefully at this sequence, you'll notice that numbers are missing. For instance, 3 is missing, 6 is missing, 10 is missing. And if you look even closer, you'll see that between any two consecutive entries in the sequence, they're either consecutive in the integers or they're skipping one single integer. So which integers are missing? Well, it turns out that there's a corresponding integer sequence obtained by computing the value x over x minus 1, so for us the square root of 2 over square root of 2 minus 1, and performing the exact same process, looking at the integer multiples of this new number and rounding down. In this case we get 3, 6, 10, 13, 17, 20, 23, and so on. Do you see what's happened? If you can't see what's happened, I'm going to weave together the blue sequence and the magenta sequence in increasing order. Now you should see it. Every integer appears once and only once. And if you keep going, this will keep happening. Maybe I got lucky, or maybe I chose square root of 2 just to have this property. So let's try again, but this time with the irrational e. Again, we take the integer multiples of the irrational e and we round them down. This time we notice that there are numbers missing from this increasing integer sequence again. And if you look closely, it looks like each consecutive pair of numbers in the list is either skipping one integer or two integers. For instance, 11 and 12 are missing between 10 and 13. We perform the same process. We compute the number e over e minus 1, take the integer multiples of that number, round down, and we get the corresponding integer sequence listed in magenta. Now we take the blue sequence and the magenta sequence again, interweave them in increasing order, and sure enough, every integer appears once and only once. It's truly amazing that this works. Can it really happen again? Go ahead and pause the video and try it with your favorite irrational number larger than 1. You could try x equals pi and z equals pi over pi minus 1. You could try x equals phi, the golden ratio, and z equals phi over phi minus 1. You could even try x equals natural log of 2 and z equals natural log of 2 over natural log of 2 minus 1. But I'm not sure that one will work out because I don't believe the natural log of 2 is larger than 1. For these other ones, what's going on here? Well, it turns out that we're witnessing a theorem known as Rayleigh's theorem in action. Rayleigh's theorem states that if you start with an irrational number x, and it has to be larger than 1, and you choose the number z to be x divided by x minus 1, which is also larger than 1 and also irrational, and then consider the two integer sequences obtained by taking integer multiples of your two irrational numbers and rounding them down, that these two integer sequences together will form a set theoretic partition of the positive integers. What that means is that each integer should appear exactly one time in exactly one of the sequences. These kinds of sequences, this idea of flooring the integer multiples of a number, are called Beatty sequences, and they are well studied, and you can look them up and find interesting things about them. So Rayleigh's theorem says that there are two Beatty sequences out there that form complementary sequences. And I just want to point out that the term complementary means that they have sort of the opposite things in common. They are set complements. It doesn't mean that they say nice things about one another, although that's fun to think about as well. So if you found this interesting, check the next video as well, where I'll explain just a little bit more about a different theorem that encompasses Rayleigh's theorem, but also allows us to find other complementary theorem sequences.